Okay, good morning, everyone. How did your homework go? Any questions about the homework? Please get going. Any questions? Number 45. Okay, we can look at that. Okay, so let's see what this is about. We have a boat sails directly toward a 150-meter skyscraper that stands on the edge of a harbor. So we have a boat. So we have here a building. And we have a boat. And the boat is sailing toward the skyscraper. So we have the skyscraper here. That's 150 meter. And we have this boat, and this boat is actually sailing toward it, going this way. Okay, so we have a boat. I'm bad at drawing, so this is a boat. This is a boat. The angular side theta of the building is the angle formed by the lines from the top and bottom of the building to the observers. So this is the angle theta. That's the angle theta, and that's the angle between the boat and the building. What's the rate of change of the angular size d theta dx when the boat is x equal 500 meters from the building? So here's the question. So that's the idea. This is the boat. The building is here. The boat is here. And this is x. X is the distance. X is the distance from the boat to the building. Okay, so that's what it is. Oops. Let me see if I can get the sharper. Very good. Now, and theta is this angle. And now the idea is as x changes, it means as the boat approaches the building, the angle theta is actually changing. Okay, so as we get closer to the building, suppose we are here, that's the angle. As we get closer, that's the angle. So the angle theta is actually changing with how far is the boat from the building. And it's actually increasing. The closer we get, the angle seems to be increasing. Okay, so as x increases, theta increases. And the question is find d theta dx. So they want me to find how fast is the angle changing with the distance. It means if I move a little bit, I am at some point, I move tiny bit, the theta is actually increasing. And the question is, how fast is it increasing per change of x? All right. So this is a problem where I really they didn't give me really any formula to work with. So to be able to know how fast is theta changing with x, I need to know a relationship, the formula, what is theta in terms of x, okay? So this problem is a little bit harder because they don't give you theta as a function of x. So can we find it though? This is the building and this is theta. Can I find an equation that relate theta and x? Now I'm gonna back to you. So this is my problem. This is my theta, which is changing with x. X is how far is the boat from the building. X changes, theta changes. So the question is, I want to find how fast theta is changing with x. So my question to you is, what's the relationship? Can you give me an equation that gives me theta as a function of x? So the question to you is, find theta as function of x. So I can find d theta dx. I need theta as function of x. Okay, was anyone able to find this? Just look at the picture this time. So they didn't give you everything just straight. Theta is the tangent inverse. Okay, let's see if your classmate is correct. I have to, so this is 150 here. So let's see what's the relationship. So a bit of trigonometry tell me that the tangent of theta is 150 over x. That's what the geometry of the picture tells me. So now what is theta? If this is the tangent, theta is the angle whose tangent is that. So theta is the tangent inverse of 150 over x. Or, as I said yesterday, I like to call it arc tangent 150 over x. Okay, so that is theta as a function of x. Now, we need d theta dx. It means we need to find the derivative of theta with respect to x. So what's d theta dx? And they want me to find it when x equal 500. Okay, but we have to wait for that. I mean, first to find when x equals 500, first I need to find the derivative. So what is the derivative here? So the derivative of tangent inverse, that's a problem where I have an inside function. That's my inside function. So the derivative is, so the inside is 150 over x. And the outside is the tangent inverse. So what is the derivative? The derivative is going to be 1 over 1 plus derivative of tangent inverse is 1 over 1 plus u squared, but evaluated at the inside. Times that. We times it by the derivative of the inside. Now, what's the derivative of the inside? So we times it by the derivative of that. Okay. So now we do a little bit of math and do a little bit of algebra to figure out the theta dx. So this is equal to 1 over 1 plus 150 over x. It gives me 150 squared over x squared and times the derivative of this. So what's the derivative of that? So if you want, we can, to find the derivative, I can rewrite it as 150 times x to the minus 1. So the derivative of that is minus 150 x to the minus 2. So the derivative is, so I'm going to have here a minus 150 x to the minus 2. So I wrote the derivative in there. All right, so another way to write this, so it's a little bit, I mean, not, actually, I will write it here because that's better. So that's going to give me minus 1 over 1 plus 150 squared over x squared times 150 over x squared. And we do the algebra a little bit. I find a common denominator down here. I will have 1 over, common denominator is x squared plus 150 squared, so divided by x squared. I use the property of fraction. The x squared will go up here, times 150 over x squared. Okay, so from here to here, I use common denominator, which is x squared plus that, over x squared, but then I flipped it because I have a fraction. So now this will simplify, and this would give me 150 over that. Okay, so it's a little bit of algebra required at this stage, of course, but the main idea is finding this relationship that exists between theta and x. And this is this relationship that will help me to find d theta dx. Now, they want me to do that at the specific value of x. So now we're going to keep this in front of us. Okay. And they want me to find d theta dx at the specific value of 500. So this really means I need to substitute 500 for x. So instead of x here, 500 square plus 150 square. And now we just have to pick up the calculator and compute that number. Did anybody manage to compute that? So I don't know. So it's minus 150. And it's divided by, so because we want to have a feeling of what is this number. It's 500 plus 150 square. So I will getting divided by 272500. So I'm getting a very, very tiny number. I'm getting minus 0.005.5045. Unless I'm doing a stupid mistake. Can anybody help me compute this? Because I feel I'm doing something not correct. Anybody can do it for me. Okay, that's what I got as well. Thank you very much. So it is equal to that. Very good. So what's the unit? Now that's the hard part. What is the unit? Back to you. I want you to think a little bit. What is the unit of this really tiny number in here? So we did all this, but I want unit so we can understand what this means. Remember, what is the unit? The easy way to find the unit of the derivative is this. You ask yourself, what is d theta dx give away the limit? What's the unit of theta? Back to you. I'm going to be asking you a lot about units, so you better get it with me because it really helps us understand. What's the unit of, so d theta dx, what's the unit of theta? What does theta represent in this problem? What does theta represent in this problem? Back to you. Theta is what? Centimeter, meter. What is theta in this problem? This is theta. What's its unit? Degrees? No. We don't work in degrees in calculus. Radian. That's radian. What's the unit of x? Back to you. What's the unit of x? That's the only way we can figure out the unit of the derivative. What's the unit of x? X is how fast is the boat from the building. So what could be a logical unit? In this book, the unit for x is meter. So that's meter, and that's radian. So the unit of the derivative is the unit of theta, which is radian, per unit of x, which is meter. That's how we figure out the unit of the derivative. So d theta dx. That's why this notation is important, to find the unit. What's the unit of theta? Radian. What's the unit of x? Meter. The unit of the derivative, because that's an average rate, it's radian per meter. That's how we're going to find the unit of the derivative. So the unit of the derivative here, d theta dx, so it means how fast is, so d theta dx, after when the boat is 500 meters away, is minus 0.0055 radian per meter. So that's meter. So intuitively, why this is helping us? Why this help us? Because this tells me the following. Intuitively, tells me the following. This is when my boat is 500 meter away from the building. This is my angle theta. And theta x is changing. Theta will change. How fast is changing? The derivative tells me that it's changing at the rate of, so it's decreasing at the rate of 0.000555 radian per meter. So that's how fast is the angle change with respect to x. So if you change x by tiny bit, so this is 500, if you change x by 1 meter, change x by 1 meter, theta is gonna change by that much radian. Very, very, very little. So when we put unit, we start interacting with the derivative as a rate. It means it starts telling me that we're at 500. We push by 1 meter, theta is changing. How much is changing by? It's changing by that much. Sorry, push by 1 meter in the positive direction. My apology. So it means that it's changing by how much? It's changing by minus 0.0005. And we know that, but it's because it's losing value. So put unit to understand the concept. Without unit, it might, this number makes no sense to us. It doesn't make sense to you or to me. When I assign unit to it, then it starts making sense. It means we are 500. Increase by a little bit, because 1 meter is very little for 500. Theta is changing. So whatever theta is here is going to lose value. How much is going to lose? It's going to lose that much radian. Very, very little, but it's going to lose value. Okay, so that's the idea. And the main idea for me now is associating unit to those objects. So how do we associate limit? I repeat, whatever you have, you ask yourself, okay, what am I computing? D theta dx. What's unit of theta? Radian. What's unit of x? Meter. What's unit of the derivative? Radian per meter. Now we can understand it. Add 1 meter, theta change. By how much? By that much. That's the meaning that we will associate to the derivative. This idea here is important. Okay, so let me move on to the other problem, number 21, 29, and 41. So let me start with 21. What this is about. Okay, so those are finding using the formula. So y equal tangent inverse of 2y squared minus 4. Oh, sorry, it's f of y. My apology, I cannot write this. So I'll start another page then. So number 21. So you have f, and they call the variable y instead of calling it x. And it's the tangent inverse of 2y squared minus 4. Okay, so here is just a problem of practicing how we evaluate the derivative and how we use our formulas. So let us keep going. So there's a problem where this is my inside, and the outside is the tangent inverse. So what is my f prime? Okay, the derivative of the outside, which is 1 over 1 plus, evaluated at the inside, times the derivative of the inside. Okay, so now I just put my inside in here. And now let us just evaluate this. So it's 1 over 1 plus 2y squared minus 4 times the derivative of that, which is 4y, and of the problem. Okay. So let's look at 29. Okay, so that's the cosine inverse. So now my function is cosine inverse of 1 over x, or the arc cosine. All right, to do that, I need to find the derivative of the inverse cosine. So this is my u in here. That's my u, that's my inside function. And the outside here is the cosine inverse. And the inside is u equal 1 over x. Okay, now what's the derivative of cosine inverse? The derivative of cosine inverse is 1 over the square root of 1 minus u squared. So now let us, minus that. So what's going to be f prime? So it's minus 1 over the square root of 1 minus the inside. Times the derivative of the inside. Okay, so this will give me minus 1 over the square root of that times. What's the derivative of 1 over x? Okay, let's do that. The derivative of 1 over x is the derivative of x to the minus 1. It means minus x to the minus 2, or minus 1 over x squared. So times minus 1 over x squared. Now I have two minuses, so this will give me 1 over x squared, the square root of 1 minus x squared. Okay, so it's really applying the chain rule fairly carefully. Okay, now let's do number 41, I think. 41, all right. Please ask questions as you move on. Okay. So the last one is number 41. So it's the equation of the tangent line at the given point. Okay, so we have the function f of x equal tangent inverse of 2x. And they want me to find equation of the tangent line at the following point. A half, and I don't want to read the other one because we don't really need it. So f at 1/2. Okay, and then we have to figure out f at 1/2 by ourselves. All right, so we need equation of the tangent line. So whatever the graph is, we have to find the equation of the tangent line. So first we need the derivative because the slope of the tangent line is the value of the derivative at 1/2. All right, so let's do that. So let me find this. Okay, what is f prime? Again, I have tangent inverse of 2x. So f prime is 1 over 1 plus the inside times the derivative of the inside. And my inside here is 2x. So it's equal to 1 over 1 plus 4x squared times 2. All right? In other words, it's 2 over 1 plus 4x squared. Now I need it at a specific value at 1/2. So what is f prime at the half? So that's the slope. So at 1/2, it's 2 over 1 plus 4 times x squared. Means times 1 over 4. 4 times 1 over 4 is a 1. So it's going to give me 2 over 2. It's 1. All right, so let's take care of the slope. Now I need the point. The point is 1/2 and the output at 1/2. So the derivative gave me the slope. Now what is f of 1/2? F of 1/2 is the tangent, arctangent of 2 times 1/2. It means that's tangent inverse of 1. Or, as I said, I like arctangent. I actually prefer arctangent because it reminds me the definition of what I'm doing. Now, arctangent of 1, it means what is the angle? Tangent of what equal to 1. That means what is the angle such that the sine over the cosine is equal to 1. Now, we did that yesterday, and the angle whose tangent is 1 is, you remember what it was? What angle have tangent 1? And you should almost memorize it because this will come up a lot with us or with you as well. So the angle whose tangent is 1 is pi over 4. Because if you remember, the sine of pi over 4 is equal to the cosine of pi over 4 is equal to 1. So the tangent, which is the sine over the is equal to square root of 2 over 2. So the tangent is 1. So this is equal pi over 4. Okay, so the point is now a half pi over 4. So finally, the equation. So the equation is fairly simple. The equation is y minus pi over 4 is the slope times x minus a half. All right, and then you can simplify it a little bit. It's x minus a half plus pi over 4, but I'm usually satisfied with that, so I don't really care about the last way. All right. Okay, so that is the problem I gave you as a worksheet, and I want you to do it for tomorrow because I would like to start a new section, and tomorrow I will definitely go over it carefully. Okay, so but please do it because it's again the idea of kind of understanding the derivative slowly, what it means, not only how to compute it. So the first thing I try to emphasize now is the unit, which gives us a feeling of really what it is, what kind of rate it gives me. Tell me how fast things are changing. And in this spirit, we're gonna start today's lecture. It's basically about how fast things change. So the problem today is section 3.11, and those problems will not be formulas anymore. So it's called related rate. Okay. All right. So what's the related rate problem are about? So I will put the problem in front of us. We will analyze it, and then we will start solving. So this is my problem. Okay. So it's the problem number 1 in your books. I did not change it. So that's my example. Suppose we have, so I'll write it, I will come back. So let us suppose oil spill from a tanker, right? From a ruptured tanker. So we have a tanker and a little bit of oil spill, and it's spread. So this oil spread in a circular pattern. Okay, so that's really my problem. So, you know, you are, let us see, in a calm sea, and you have this tanker, and we have oil, which is a leak from the tanker, and it starts spreading. So you have a drop of oil, and then imagine you are in a perfect universe, and it starts spreading in a circular pattern. So it starts spreading like this, in a circle, in a circle, in a circle. That's really how it starts spreading. All right. And here's the problem. Suppose the radius of the circle. Suppose the radius of the circle. So if the radius of the oil spills increases, so suppose the radius increases at a constant rate of, let us say, 2 meters per second. Okay, every word is going to be analyzed. Every word is going to be analyzed in a second. And my question is the following. How fast is the area of the spill? How fast is the area of the spill increasing when the radius is first 2 meters, second 6 meters. Okay, so I'll read the problem a little bit. We're going to interact with it, and we're going to try to see how we do, or how we solve it. So we have a tanker, it ruptured, a drop of oil fell, and it started spreading in a circle, spreading like this. So it spread and spread and spread in a circular pattern. Now, as it's spreading, the radius is increasing. Okay, the radius is increasing. And the radius is increasing at a constant rate of 2 meters per second. So it's increasing with time. So the second here, that's a time. And increase at a constant rate of 2 meters per second. So already what information, what does this mean? It means the radius every second, it decreasing by 2 meters. So it started at 0. After 1 second, it decreased by 2. Another second, so we're going to draw another picture to reflect that. It increased by 2, increased by 2, increased by 2. So if I draw, basically, this is the time, and this is the radius, means that my radius is increasing at a constant rate of 2 meters per second. So the graph is actually a linear graph. So that's how the radius is changing with time. So now if I ask you, what is the derivative of the radius with respect to time? In this specific scenario, it's a constant rate. So what's the derivative of the radius with respect to time? What is your answer? So how fast is the radius changing with time? So what's the derivative of the radius with respect to time? It's increasing at this constant rate, 2 meters per second. It means this is the radius at 0. Every second is increasing by 2 meters. Every second by 2 meters. So the derivative is equal to 2. So increasing at a constant rate, this is really telling me that that's how fast the radius is changing. So that's the questions about the derivative of the radius. Now, my question is, how fast is the area of the spill increasing? So as time goes by, what's happening? The radius is increasing with time. As the radius increases with time, the area of this is also increasing with time. It's increasing, increasing, increasing. And my question is, how fast is the area of the spill increasing? Any question about how fast is really a question about the derivative. So it means with respect to time, how fast is the area increasing? Is it increasing by 1 centimeter square per second, 2 centimeters square per second, when the radius is 2 meters? So that's really the idea here. So the word related rate is, we have two quantities that in a way are related. I know how fast one of them is changing with respect to time. Our underlying variable will be always time. I want to know how fast the other one is changing. Before even we do this question, let me ask you the following, and please try to answer. So I'm going to describe the picture a tiny bit again. So we have at 0 right here, the spill, that's the oil. It's spilling and it's spreading. After 1 second, the radius grew. The radius is growing at a rate of 2 meters per second. So after, that's at 0, after 1 second, this grew. So this is my radius, this is my spill after 1 second. So I'm going to write here t equal to 1, because that's really the picture for us. Okay, that's the radius. Another second later, the radius is actually keep growing at the same rate. So this is now, it already grew by 2 meters. Now the radius doubled basically in this scenario because it grew by 2. So another 2 attached to it here. So right now, this is my area. And write this. So the area grew. So that's really my circle. So my area between, so this is what's happening at t equal to 2. Okay, so at t equal to 1, that's the area of my spill. At t equal to 2, that's the area. So the area changed by that much. It grew by that much. So that's really the change of area for t between, if you want, 1 and 2. That's by how much it grew. So this little piece here. Okay. Then what's happening after that? A second later, my radius was increased by 2. So the radius is increasing at a constant rate. So that's 2, it's 4, it's increasing at a constant rate. So now my radius is right there. And my area actually, of course, now my area grew. So that's my area. Okay, so that's the area at t equal to 3. Okay, so between the time t equal to 2, between here and t equal to 3, my area grew by that much. Okay, just have, that's the picture. So that's really my area. My first question I'm going to ask you is the following. Is the area growing at a constant rate? Is the area growing at the constant rate? The radius is, because that's given to us. Every second, the radius increases by 2 because it's a constant rate. However, is the area growing at a constant rate? Absolutely not, as you guys are mentioning, because between 1 and 2, it increased by this band here. So this band tells me by how much the area increased between 1 and 2. And this bigger band, the red one, is showing me how much it grew between 2 and 3. So the radius, the area, is not growing at the constant rate. So it's really changing. So the question is, how fast is it growing? So question number 2 to you, before we really even do this problem. Question number 2 for you is the following. Okay, when the radius is 2, it means t equal 1. And I want you to compare how fast, intuitively, we're not giving answer. If I tell you when was the area growing faster? Here at t r equal to 2 or at r equal to 6. It means when the radius is 6, it means t is 3. And okay, when was the area growing faster? Here or here? So with respect to time. So let us think a little bit, what do I mean when was it growing faster? Remember, time is, think of that as a speed. When was the area going faster, speeding up in terms of time? Again, we're going to rely on the picture a little bit so you understand, how we're going to do that. So let us think picture-wise. When was the area growing faster? Here and here. So I'm going to say, okay, after 1 second, it's here. If I take a little bit more time, add a little bit more time, tiny bit of time, how much was the area changing? So suppose I take t to be very little, 1/10 of a second. Okay. Now the radius is changing by 2 meters per second. So in 1/10, the radius changed by 2/10, that much, a little bit. So suppose here the radius changed a little bit. The area is going to change by that much. So if I am at 2 and I change after 1/10 of a second, since the radius is changing at a constant rate, the radius is changed by 2/10 because it's 2 per second. So in 1/10 of a second, it's going to change by 2/10. The area changed that much. When I am right here at 6, and I change by the same amount of time, 1/10, the radius is changing by this, since the radius is changing at a constant rate, it's changing by 2/10. But how about the area? Is the area changing more or less? So when the time changed by 1/10 of a second, from here, the area changed by that much. And when I am right there, after a little bit of time, the area changed by that much. Means the area is changing faster at 6 than it is changing at 2. Add a little bit of time, we change that much. Add a little bit of time, I'm changing a lot. So the area is changing way faster here than it's changing here. So what do I mean by changing with respect to time? It means if you add a little bit of time here, and a little bit of time. When is the area changing more? Definitely it's changing more right there. So now the question here is, how fast is the area of the spill increasing? Now the underlying here, how fast is it increasing, even though they are not putting it, how fast is increasing with time? So when the radius is, when I am right here, how fast is this area increasing? It means with time. So it means if I change time a little bit, how fast was the area changing? So how fast the area changing is actually a question about what's the derivative of the area with respect to time. That's what how fast means. And they want me to find it when r is 2 and when r is 6. Because that's intuitively what related rate is. So I have two things that are varying in this problem with time. I have the rates that's changing with time, and I have the area that's changing with time. Time is my underlying variable. I know how fast the radius change, 2 meters per second. It's a constant change. What I'm after is how fast the area is changing. And we know that's not changing at a constant rate. The picture tells me it's not the case. Even if though the radius will, the area does. So how do we treat those type of problems? Okay, so that's gonna learn how to do them. So the question is, how fast is the area of the spill increasing with time? Any question that asks you how fast is the area increasing with time is a question about the derivative of the area with respect to time. Because the unit here is going to be unit of area, centimeters squared, for unit of time, which is second. That's the unit of how fast things changing, how much per second the area change. So now how are we going to solve this problem? It means how fast is it changing here? 1 centimeter square per second, 2 centimeters square per second, how fast? And even here, when r is 6, okay, that's the radius now, all right? And then we add a little bit of time. How fast is the area gonna change? Again, 2 centimeters square per second, 5 centimeters square. That's really what I am after. So let's see how we're gonna solve those type of problems. And we're gonna have not an algorithm, but an idea of the steps we have to go through. Okay, the first step is read the problem 5 times. Okay, that's really the first step. I don't have, okay. Did you guys copy this? Yes or no? Are you with me? Okay, please stay with me. Put your coffee in front of you like I am doing. All right, so how are we gonna do this problem? The first step is read the problem 5 times till you understand it. That's crucial. All right. The second step is what are, most of the time here, everything we're gonna be working with in this section will change with time. So time is gonna be my underlying variable. But I have to introduce what is changing here. In my problem, 2 things are changing. The radius is changing and the area is changing. So we're gonna introduce 2 variables. So I'm gonna call A of t the area of the circle at time t. Okay, and then another thing that's changing is the radius. So I'm gonna call radius of the circle at time t. Okay, that's what's changing with time, the area and the radius. The second step is, after we read the problem, we have to say, what is the problem given to us? Okay, what's the problem? And what are the unknown, or what is we're looking for? Okay. All right, the given to us here, so most of those problems will involve the following. You will know how fast one of the variable is, and you'll have to find how fast the other one is. How fast means, you know, the derivative of one, you need to find the derivative of the other. And both of them change with time. That's my variable here, time. Now, what's given to us is that the radius is changing. The radius is changing at a constant rate of 2 meters per second. That's what's really given to us. So I know how fast the radius is changing. What is the unknown? It means what is it we want? What they want me to know is how fast the area is changing. That's really what they want me to know. And they want me to know this for two values of r. It means when r hit 2 meters, and then when r hit 6 meters. Okay, so they want me to do that for different values of r, right? So I don't have formulas really to work with, as you realize, a lot of formulas, and how I'm gonna solve all this unknown stuff. All right, the first step here is to find an equation. So that's where the word related rate is gonna come from. So my first step will be find an equation that relate the variable. Find an equation that relate the variables. So what is the relationship between those variables? Because they have to be related, otherwise this is nonsense. Okay, they have to be related. So what's the relationship between the variables? My variables are area and the radius. Okay, and definitely as the radius gets larger, the area will change. So they're definitely related. But what's the relationship between them? What's the equation that relates them? Right? The area for every moment in time, regardless what t is, the area is always, regardless what t is, it's pi times r squared, right? That's really what's happening, no matter what t is. So now to emphasize the idea that all of them change with time, or I'm going to write it like this. No matter what t is, no matter what t is, the area is pi times the radius, which is itself a function of time. So that's the relationship between the variable that holds true regardless what t is. No matter what t is, that's the relationship between them. Now, what we want actually is a relation between their derivative, because I'm having info about the derivative of r, how fast this one changed. I want to know how fast this one changed. So I have to get to the derivative because that's really what I care about. So now what we're going to do is we're going to differentiate. Now the idea is we're going to differentiate with respect to time. Time is my underlying with respect to time, to find an equation that relate the rates themselves, to find an equation that, and that's where the word related rate, that relate, quote unquote, the derivatives. So I want to find a relationship between the rates. That's really what I want. So the way we're going to do it is, okay, this is a function of time. I don't know what A exactly is, but I'm not going to really worry about the formula. And R is a function of time. I'm not going to worry about the exact formula of it. I'm going to differentiate both with respect to time. So let us do the differentiation. All right. A is a function of time. This tells me that it means the derivative of A with respect to time is equal to. And now the hard part and the most interesting part. Remember, this is not R. This is something that is a function of time. So there is not an R of R here. It's not R. Is a function of time that I'm not going to even though in this problem it's easy to find a formula for it, but I'm going to pretend I don't know the formula, because for the other problem, we really don't know the formula. So what's the derivative of that with respect to time? Can anybody tell me? So this is a function of time. So what's its derivative? What does the chain rule tells us? What's the derivative of that? You can think of this as your inside function. And so the derivative is going to be pi, that's my constant. What's the derivative of r of t? So that's my inside. That's really my inside. So it's the derivative of u squared, which is 2 times the r, times the derivative of the inside, but I'm going to write it dr dt. because I want to emphasize it's how fast the radius was changing with time. So that's, or sometimes it means, or we can suppress at some point the t here to make it a little bit easier, and this would become 2 pi r times dr dt. So that's the relationship between the rate. So that's the equation that if I know the rate of one, I will be able to find the rate of the other. So we differentiate with respect to time to find an equation that relate the derivative. Now, once we do that, I zoom in at what they want me to do. So now that's the last step, is use the given to find the unknown. Use the given to find, that's the last step of the process, to find the unknown. So that's my last step. Okay, so once I find the relationship between the derivative, then I have to use what's given to us to find the unknown. Now, what is given to us? What's given to us is that I know how fast the radius change, 2 meters per second. Okay, and I need the unknown is dA dt, that's the unknown, for 2 values of t, for 2 values of r, when r is 2 and when r is 6. So we're gonna do each one of them separately and we're almost done. All right, let's see what it is. So let me take my formula, my relationship, and do it. Sorry. Okay, so let's see here. So that's my relationship, that's it. So I have dA dt. So now here I'm gonna find r equal to 2. So the first problem is equal to 2 pi r dr dt. That's the one I want when r is 2. And that's what's given. So it's gonna be equal to 2 pi when r is 2, so that's the value of r, times the r dt, which is 2. And that's going to give me so it's going to give 8 pi, which is, I want a number. I mean, usually in your quizzes, you can give 8 pi, I don't care. But right now I want a number just so I can make a little bit of sense out of it. So it means almost 25.13. What is the unit? What is the unit? I just told you how to find the unit because that's how you're going to make sense out of it. What is the unit in here? dA dt.
Centimeters squared per second.
Crucial. Now you can make sense out of it. It's centimeter square, unit of area, per second, unit of time. This tells you that when the radius is 2, the area is increasing. How fast was it increasing? Means once we are here, a little bit of time, the area will increase. At what rate it's increasing? At the rate of 25.13 centimeters square per second. It means we're right there. A little bit later, 1 second later, the area increased. By how much? By 25.13. Half a second later, it increased by how much? Almost half of 25. Okay, like 12 point something. 1/4 by 1/4 of that much. So this is the area is really giving you how fast it's increasing at 2. Now at 6, it's going to increase faster. And let us see at 6. So after r equal to 6, how fast it is increasing. And we're done. The formula is the same. So now once we find the relationship, I can plug in any value here. It's going to be 2 pi times 6 times 2. Give me 2 times 6, that's 12, 24 pi. And I wouldn't like, as I said, I like to compute those because this will make more sense to you. Times pi. So that's going to give me almost 75.39. Again, the unit, it's centimeters square per second. So this is also again tell me that at 6, when the radius hits 6, when the radius is 6, The area starts increasing at a very much faster rate at 75 centimeters square per second. So even the radius is moving at a constant rate, but the area is really growing at a faster rate. So back to my picture, this is 6. At this here, the rate is 75 centimeters square per second. So we are right here, the radius. After 1 second, the area is growing by almost 75. After half a second, it's half of 75. The smaller the time you take, the better approximation we have for how much the area is going to change. Okay, so definitely at a much faster rate. Right? So I will do only this problem, and I'm going to assign for tomorrow basically like 2 or 3 problems at most, very similar to this one. And tomorrow we'll do more, more harder problem if you want. And you would spend the whole hour basically working on those problems because they are not as simple as the one we've done before. And the worksheet I gave you, please do it. So tomorrow I will start with the worksheet, and I will then pick up all your questions, and we will do more problems along those lines. Right? Any questions, anybody? Okay, good luck. Bye-bye. See you tomorrow.